So the last time we met, which was a week and a half ago or something like that, we finished the treatment of fermions, right? We looked on the Fermi distribution, we computed the Fermi level, we understood why in room temperatures where there are many electrons present, the interactions are not so important, or correlations. And now I want to treat very similar case, but absolutely distinctive, which also quantum particles, but not fermions, but bosons. So it's boson liquid / gas. Basically, if we see what happens for fermions, and there is an interesting behavior, and the Fermi level determines everything when we use the grand canonical representation in order to develop our results, and it's the accumulation of events that gives rise to everything. So if you remember, if you look on the energetic spectrum, we know that, well, all the fermions sit one on top of each other, and it's accumulation of many, many events, of many, many particles that contribute something. Okay, so if you want to remember something about fermions, remember this plot over here. They stack one on top of each other, and eventually the Fermi level is somewhere up there. All the dynamics or all the contributions, basically, where are the energies that sometimes are open and sometimes are filled, is extremely high. So it's the contribution of everybody that leads to something, right? We will see that for bosons, the situation is quite different. Okay, so first of all, what we assume there are, for those bosons, there are no interactions. No interactions. Okay. Now, for fermions, it was exactly the same thing that we assumed, but for fermions that there were, in principle, extremely strong interactions in the form of Pauli exclusion principle. But for bosons, there are no such thing as Pauli exclusion principle, right? So if I'm plotting, if I'm going to get back to this example, let's assume that I have epsilon 1, and I will have epsilon 2, and I will have epsilon 3. Right? If this is what I have in my system, in principle, I can put as much particles as I like at each level. Right? So if they are not interacting, right, I can put here particle number 1, and particle number 2, and particle number 3, and particle number 4, and another particle over here, another particle over here. There's no limitation, right? So strict restriction for fermions, absolutely no restriction for bosons. Okay? So this is the huge difference between the two. If beforehand I can only, if you're forgetting about the degeneracy due to spins, okay? So if I'm forgetting about the degeneracy of spins, I can say beforehand I could have either 0 particles per level or 1. Now I can have 0, 1, 2, 3, 4, 5, and any countable number of particles at each level. Okay. Now, what happens to my grand canonical representation? So I don't want to say, oh, the particles are completely independent. I want to use the same representation as I used for fermions. In what sense? I'm saying the following. I decided, or the nice representation, the grand canonical representation for fermions appeared when I wasn't looking on the independence of particles. I was looking on the independence of energetic levels. And I constructed the partition function as a partition function factorized on the different levels that I have inside my system, and not on the different particles. I want to use the same idea for bosons. Okay? So it's a grand canonical representation I have no limitations on the number of particles per each level, and I don't have a general restriction for the number of particles. So this is similar to fermions, right? So for fermions, I also haven't restricted the number of particles in my system. Okay, there was restriction on per level, but not global restriction. The same goes here. There is no global restriction. Okay, so if we start from scratch and we want to say, right, so what is the partition function? So the partition function for grand canonical representation, it's always the same. We go and we count over all the different possible states of the system. Okay, we put here E beta, EI minus mu and I. Okay, beta is 1 over k boson T, mu is the chemical potential, and each state is defined by this set of EI and NI. Okay? Now, what I have done for the fermions, I said the following thing. So I said, all right, so what is EI? EI is the number of particles that are sitting at the level epsilon 1 multiplied by epsilon 1 E1 plus the number of particles that are sitting at the state at level 2 epsilon 2 plus the number of particles that are sitting at level 3 multiplied by n3 and etc, 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 etc. Okay? Doesn't really matter how many levels I have. This is my representation. Okay? So the quantum numbers, the integer numbers, are n1, n2, n3, n4, n5, n6, and 7. Great. Now what is Ni? Ni is just the total number of particles that I have at this specific level. What is the total number of particles that I have at specific specific state? Is the number of particles that I have at level epsilon 1, which is n1, plus the number of particles that I have at level epsilon 2, which is n2, plus the number of particles that I have at level 3, which is n3, etc, 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 etc. We use the same representation for fermions, and there we had a restriction. Oh, n1 can be either 0 or 1. But for bosons, n1 can be 0, 1, 2, 3, 4, 5, 6, 7, whatever number you like. Okay? So goes for n2, so goes for n3, etc, etc, etc. Okay, now what I want to write is this term, right? So EI minus mu Ni, which is, let's write it as a sum, a summation over j, right? Which is nj epsilon j. This is EI minus a sum over j and j. This is Ni. Okay. Now time use. Okay. So I write it down as a sum over j and j epsilon j minus mu. And j can be whatever I like. So for each specific state, okay, each specific state, what determines the specific state? All the different occupation numbers. Occupation number of level j. I just count the total number of particles that are here, are there, here. I can go over all my different levels, and I know this for specific values of all the nj's. This determines the state, a specific state of the system. Now, because there are no interactions, and because there are no Pauli explosion principle, I do the following thing. We look again on our z. It is a sum over I, e to the power minus beta. Now, instead of ei minus mu ni, what I write? I write sum of j, nj, epsilon j, minus mu. Sum over j, nj, epsilon j, minus mu. So I have a summation in the exponent. The sum in the exponent I translate into a multiplication of the exponents. So I have a sum over all the possible j's, okay? And here I'm going to have, this is I. A sum over all the different states I that I have in my system. A summation of all the j e to the power minus beta and j epsilon j minus mu. Now, let's define Zj, which is a sum of all possible j's, the sum of all possible nj's. Nj goes from 0 to infinity, e to the power of beta, nj epsilon j minus mu. Now, this is what? This is a partition function of a single level. Partition function of level j. Right? I look on all the top occupation numbers of this specific level. It determines these different states for this specific level, and I count up all the different possible states of this level. Okay. Now notice something, that nj they're all independent. N1 doesn't care about N2, N2 doesn't care about N3, N3 doesn't care about N451. They are all independent because we implicitly stated there are no interactions and there are no Pauli exclusion principle. So this guy, when I have all the different multiplications and I sum over all the possible values of all the different nj's, I simply say, well, the only thing that happens, all this summation and multiplication is transformed into multiplication over all the different nj's. Z equals to multiplication g from 1 to infinity over zj. This is our factorization. This is what we're looking for. But again, as for fermions, the factorization is not over the different particles. The number of particles is not restricted. We don't know how many particles we have in our system. The factorization is over different levels, energetic levels that we have in our system. This is important. The only thing that I need to do is to go for each specific level, compute the partition function of this specific level, and then multiply all those partition functions together. Okay? Yes? Okay, so what I have over here, so the question is what happens to the summation of I? What this object represents? This object, I go and I count over all the different N1, N2, N3, etc., etc. This is the summation. And I count all the different possible N1s and N2s and N3s and N4s. So how can I count? What I'm doing, because they are all independent, I'm saying the following thing. I can count first of all the possible N1s and keep N2, N3, N4, and 5 constant. It will factorize Z1 and we'll get it out. Then I will count on over all the possible N2s. It will factorize Z2 and I'll get it out. Then I'll count on all the possible N3s. It will factorize Z3 and I'll get it out. It's just how I count. Okay? So go back as we did it for fermions. Okay? I explicitly showed there how I factorize each Z1 and Z2 out, and it's done exactly in the same thing.
למה דרך עברת מסכימה על I לסכימה על J? לא היה לנו גם וגם, בשורה למעלה.
Yep.
סכימה על I על הכל, ואז
Yep.
בתוך האקספוננט שלך סכימה על J.
Yep. So, what is this multiplication and counting?
ההכפלה היא על I או על J?
This is J. This is J.
הסכימה היא על I.
The summation is I. So, all of this is a multiplication. So if you would like to do the following thing over here, okay? I'm counting, let's go to this representation. I'm counting over all the different states. So what I'm actually doing, I'm choosing N1 and N2 and N3 and N4 and N5 and N6 and N7, okay? And then I count of all the different representations of this huge vector. Now I'm saying the following thing. Let's keep N2 and N3 and N4 everybody together. So I have Z and this guy, sum of I, e to the power beta, sum over j and j, epsilon j minus mu and j, minus mu. Okay. This is what I have. So I'm saying let's skip N2, N3, and N4, and 5, and 7. So I have here sum over I, e to the power minus beta, N1, epsilon 1 minus mu, multiplied by e to the power minus beta, a summation j goes from 2 to infinity, and j, epsilon j minus mu. Is it a kosher rule? Great. When I'm summing over here, I'm going to say the following thing. I'm keeping, so the summation now is, let's sum first of all the possible n1s, and keeping all the nj's over here constant. Okay? So I'm doing the following thing. It is e to the power minus beta 1 epsilon 1 minus mu multiplied by all the sums, I call it I prime, okay, where all those are something and then 1 is constant. E to the power minus beta, a summation j goes from 2 to infinity, and j, epsilon j minus mu. Plus, let's continue it over here. Plus, e to the power minus beta multiplied by 2, this is when I'm taking n1 to be 2, epsilon 1 minus mu multiplied by summation over I prime, e to the power minus beta, a summation of j goes from 2 to infinity, nj, epsilon j minus mu, plus e to the power minus beta multiplied by 3, epsilon 1 minus mu, multiplied by the same thing, plus e to the power minus beta multiplied by 4, epsilon 1 minus mu, multiplied by the same thing. And you start to see the structure, right? It's always something that it's not including n1, multiplied by e to the power minus beta 1 epsilon 1 minus mu. Something that it's not including epsilon n1, multiplied by this factor. Now, again here, and again here. So we can take this as a prefactor, okay? I'll write it down over here. And here I'm going to have a sum, n1 goes from 0 to infinity, e to the power minus beta, n1, epsilon 1 minus mu. Do you agree with me? This is z1 multiplied by this something. Okay? Now I repeat the process again. I'm taking this something, and I'm doing this, I'm factorizing out n2. And I'm doing factorizing out n3, and n4, and etc., etc. And eventually, I will get just factorizations of all those guys. Okay? So it's the matter of summation. The summation over all the different vectors, possible values of this vector. But how I can sum it? I can keep everybody constant, sum over only n1. We'll get this z1 outside of the sum. Then, in the remaining sum, I will cause n3 and above to be constant, and I factorize over n2, etc., etc., etc. Okay? So, I agree with you, it's hard to see how I'm jumping from here to here. I assume that you remember how we done it for fermions, but this is the process, right? Okay. So what we have now? We have, let's write it down again. We have the partition function, z, which is a multiplication. J goes from 1 to basically infinity, depends on how many states do we have, of Zj. Well, Zj equals a summation of nj goes from 0 to infinity, e to the power minus beta, nj epsilon j minus mu. Great. And here nj is just a dummy variable for my sum. So if we understand this correctly, the only thing that we need to explore is the behavior of a single z, right? It's going to be determined by epsilon j, the values of b, and values of mu. Those are constants, right? I have a specific energetic structure, I have a specific temperature, I have a specific chemical potential, okay? And I can explore each guy over here. Okay? So basically we can look just on the behavior of z j, and then from this behavior we can understand something about the global properties of the system. Okay? So this is what's interesting. Specifically what is interesting, if you remember, I'm trying to make this analogy to fermions, is what happens to the average number of particles at each level. Okay? If we look on this specific quantity, so for fermions, the moment when we started to calculate nj, okay, so nj average number of particles at level j. Okay. So for fermions, that led us to the Fermi distribution. That led us to the behavior, if you remember, of the sigmoid function. Okay. There was epsilon j divided by mu, and we had nj. So this is fermions. You know what? Let's plot it over here. Whenever you're trying to fit something in a small drawing, a rule of thumb, draw it on a larger scale. So, fermions. There was a nice behavior. We looked on epsilon j divided by mu. We looked on nj, which was also the probability of occupation of a specific level. Why? Because there it was either 0 or 1. So nj for fermions, it's also the probability to occupy, occupation probability. Okay. And it had this nice transition for very low temperatures. It was a step function. Okay, this is t goes to 0. And then it brought it up. So it was this. And it was like this as a function of temperature. Okay? And we based everything on the behavior of the average number of particles, or the occupation probability, for the fermions. And now for fermions, this nj average, it is 1 over 1 plus e to the power beta epsilon j minus mu. Okay. This is what we got. This is the Fermi distribution, if you like. Okay. What happens for the bosons? You can calculate it. Now, it's also we have a factorization. So the moment that we know what happens at each specific level, we can out of this behavior understand something what happens on the global level. Okay? So the first idea is, great, let's see what happens based on a specific level, what happens to this average number of particles. Now for fermions, we obtain this transition 0, 1, okay, and some spreading out of this behavior. This is what led to the Fermi distribution. That's what led to accumulation of different effects. Let's see what happens at bosons. For bosons, we expect something maybe different because there are no Pauli exclusion principle. Okay, so let's see what happens. So, what is NJ? What does it say? What is NJ? How we calculate it? Sum over what? NJ goes from 0 to infinity, right? We sum over all the possible values of NJ. Here we have NJ. Multiply the probability that this specific level will have exactly NJ particles. What is the probability? We have a grand canonical representation, right? So it is e to the power of beta nj epsilon j minus mu divided by zj. This is the average number of particles for the system, right? Probability. Average based on probability. This is a probability. Those are the different values. We just sum over everything, and that's it. How we calculate this guy? Feynman, yeah, it's very easy. Now, but Feynman with respect to what? So first of all, let's get rid of zj. So 1 over zj over here. Here we have nj goes from 0 to infinity. Here you have bn e to the power minus beta nj epsilon j minus mu. And with respect to what we are going to differentiate? What do you say?
Beta epsilon j.
So we want to with respect to epsilon j minus mu, with respect to beta, or with respect to everything?
Everything without NJ.
Okay, so everything without NJ. So I write it down as 1 over zj, sum nj goes from 0 to infinity, nj, and I sign up that beta epsilon j minus mu equals to x. Right? So I have minus nj x. Right? This is what I have. Look on this guy. So this is the Feynman trick, and say, well, this is just minus the derivative with respect to x. So nj e to the power minus nj x equals to minus d to dx e to the power minus nj x. Okay? So I have 1 over zj, a summation nj goes from 0 to infinity, minus d to dx e to the power minus n gx. I take minus d to dx out, so I have 1 over zj minus d to dx. So remember, now it's crucial not to actually interchange the order, because zj somehow depends on beta epsilon j and minus mu. So it's important to keep it in this specific order. What I have here, I have a summation nj goes from 0 to infinity, e to the power minus x to the power of ng. What is this guy?
Geometric sum.
It's a geometric sum. Okay? So this is a geometric sum. We know what is the sum of a geometric series. Now look on this. This is e to some specific power, minus x. So we say the following nice thing. So we have minus 1 over zj d to dx multiplied, it's an infinite geometric sum. It's important because in principle we have infinite number of particles per level, right? We have no restriction. This is the crucial thing. In canonical ensemble, there is a given number of particles. This is a constraint that we always have to satisfy. Constraints, no matter what, make life difficult. Okay? We remove the constraints somehow, and a lot of math problems become, well, much more easier. That's what's happening over here. If we had a specific constraint, we would have a limitation over different nj's, right? Because it will be restricted by the total number of particles. Moreover, if we had a given number of particles, the different levels couldn't be independent. Because if I put here one particle, it means that I cannot put it somewhere else. This is why we are using the grand canonical representation. Yes?
איך אתה יודע להגיד ש-x הוא לא שלילי? ואז הדבר הזה...
Great question. So why is it x is positive or negative? We'll deal it in a second. Let's assume that it's kosher now. Let's assume that it's kosher. But it's basically, we'll introduce specific problems on epsilon j and d. Okay? Alright, so what we have over here, 1 over 1 minus, right, e to the power minus x. Right? This is what we have. Let's take the derivative of this guy. So it is minus 1 over zj d to dx over, you know what? Wait a second. Because you see, what is this guy? It's always the straight because what is zj? Before doing the derivative, what is zj? It's exactly this. So n j goes from 0 to infinity, e to the power minus x, this is our x, to the power ng. Right? Or let's write it explicitly. E to the power minus beta n j epsilon j minus mu. Remember that beta epsilon j minus mu equals to x. So this is just a summation n j goes from 0 to infinity, e to the power minus x to the power of n j. Okay. So what we obtain is that nj average, it is simply minus d to dx a log of zj, which is minus d to dx a log of 1 over 1 minus e to the power minus x. Which is d to dx log of 1 minus e to the power minus x. Now we take a derivative out of this guy, and it gives us 1 over 1 minus e to the power minus x multiplied by e to the power minus x minus multiplied by minus 1. This is 1 over e to the power x minus 1. In total, nj, average, we substitute instead of x, beta epsilon j minus mu, x equals beta epsilon j minus mu, nj equals to 1 over e to the power beta epsilon j minus mu minus 1. So this is bosons. What was the occupation probability or the total average number of particles for fermions? Nj. So this is B, this is Fermi. Do you remember what was the result?
Exactly the same plus 1.
The same plus 1. E to the power beta epsilon j minus mu plus 1. This is Fermions. We look on this, well, this is the only difference, right? Also, this is, you called it during TAs, this is like the Fermi distribution, because it will appear in different calculations of the total number of particles, of the grand canonical potential, etc., etc. The same will happen for this. This is a Bose, called Bose-Einstein distribution. So this is Fermi-Dirac, this is Bose-Einstein. And they say, well, that's the only difference. Plus 1, minus 1, who cares, right? Who cares? But it's very important. And I think what Gonan mentioned beforehand. How do I know in all of this, all over here, right? I summed up a geometric series where I have e to the power minus x. And the series explodes the moment that x is larger than, or I'm sorry, smaller than 0. Okay? Now, I know that the average number of particles for each given energetic level should be something. It cannot be infinity. So how I can overcome this issue? I have a limitation that comes out of all this situation. It basically says that for all j, no matter what is j, epsilon j minus mu is greater than 0. Or epsilon j greater than mu. Because it happens to any j or any energetic structure or level, we have a limitation for bosons. And the limitation is that the chemical potential should be less than the lowest energetic level in our system. Right? If beforehand, the chemical potential for fermions was something that must be above the lowest level, right? Because it determined some specific energetic level in the middle of things. For bosons, it's the other way around. For bosons, in order for the average number of particles not to explode, the chemical potential always have to be smaller than all the energetic levels. And if, for example, our ground state is at the energy 0, chemical potential for the system of bosons, non-interacting bosons, have to be negative. Okay? It's going to be important. Now, we will continue this tomorrow, but the crucial thing that I want you to remember is that while this function is always well behaved and it's always nice, although it's used in different applications and it has a cool name in the AI community like a sigmoid today, this guy has a divergence. From the moment that we have a divergence, when it has a divergence, for example, if we start our lowest energetic level is 0, okay? When the chemical potential approaches 0, this guy can become very, very, very large. Okay? And this will provide us a fantastic new physics. I won't describe it today to you, but actually this divergence says something much more interesting than the nice behavior of the fermions. It will create some sort of a new phase for a system. It's this behavior over here, this divergence. The moment it's almost in any physical situation, the moment that we have some sort of criticality, some sort of divergent parameters, divergent behavior, means that new physics will crash into our world and say something, oh, there is a new behavior. So this divergency that we see that can be present over here will give rise to some phenomena that is known as Bose-Einstein condensation. I will describe you this phenomena tomorrow. See you all. One more thing. Since the classes last week were cancelled, I spoke to Oz and I understood that you decided that Thursday between 12 and 3 is the preferable option. There are going to be class in room 303. I will publish a note about it. It's going to be recorded and also shown in YouTube at live.
איזה שעה? עד איזה שעה?
Between 12 and 3. There's going to be a break in between.
On Thursday? On Thursday?
On Thursday.
אני אומר להגיע לאנליטית או לסטאס.
איי.
לא, בגבול שאני...
כן.
אני כאילו מבין שאם אפסילון גדול ממיו אז הטור מתבדר.
הטור מתכנס.
כן. אבל כאילו, למה אנחנו מציעים מזה? שיש כלים כאילו טורים מתבדרים כמו, לא יודע, בורוב,
לא, אתה צריך לסכום את זה בצורה אחרת, פה זה סכימה כזאת. אתה צריך לסכום את זה בצורה אחרת. כל הבורב והאוילר וכל הדברים האלה, אתה מבין מההתבדרות משהו לגבי התנהגות של הפונקציה. תכלס, כל הסכמה הזאת של הבורב זה כשיש לך פונקציה ואתה הצגת אותה לא נכון. פה זה משהו אחר.